And our last talk of the session will be given by Ward Howard, who is joining us from Colorado.
Can you hear me okay? Great. I recognize that I'm the last thing standing between you and lunch. I'm also the last thing standing between me and lunch, so let's bear ourselves together here. I probably don't need to justify why TRAPPIST-1 is potentially our best chance of characterizing secondary atmospheres of rocky exoplanets by this point in the conference, but if I were to try to do that, I would just remind you of this plot showing that there are two main reasons for this. TRAPPIST-1 is a multi-planet system, meaning we can explore the effect of the host star at different distances from the star with this multi-planet nature, and then we also have a very high transmission spectroscopy metric for the TRAPPIST-1 system compared to other high-priority targets. However, time variable contamination from spots and from flares is contaminating these observations at levels up to an order of magnitude greater than that of the planet atmospheres, which we've also talked quite a lot about so far. But where I'll be focusing this talk is where we spent a lot of time thinking about what needs to be done to correct the slowly varying contamination of the spots and the faculae. There's been relatively less attention paid to how to correct the contamination due to the rapidly varying contamination from the flares. And so just to give an illustration of the problem, here I have a movie showing several contaminated transits where I'm highlighting the relative amount of contamination throughout the transit in red. And then I'm also showing what the non-contaminated transit should look like according to a Batman model, so that you can see that the flares are messing with both our limb darkening coefficients and also our transit baseline and a number of other things. And so this could lead to potentially some skepticism. Is TRAPPIST-1 really our best chance of characterizing terrestrial atmospheres? And while I would understand the reasons for that pessimism, I'm actually here to encourage you. I think it still is. I actually see these flares not so much as a nuisance, but actually as an opportunity. First, an opportunity to characterize stellar flares at infrared wavelengths for the first time, but then secondarily, to be able to use what we've learned characterizing those flares to separate the stellar and the planetary signals. And for the rest of this talk, I'll be focusing on this subset of the TRAPPIST-1 data set, which was obtained by the NEAT collaboration, which is PI'd by David Lafreniere. And I'll be focusing specifically on these points I've highlighted here in green, and the reason for that is twofold. One, they have very nice high signal-to-noise flare signals, and then the second reason is that we have a pretty good idea of what the physics of these flare events is. To give an example of that, flares tend to spike in temperature and then cool, and during these times we see that pattern. Even though the flux continues to decrease in the gray times, sometimes the temperature starts to go back up due to secondary heating processes we don't fully understand yet, so that's going to be future work. And so the benefit of this is just the green points alone give us 189 integrations or 5.5 hours of monitoring time that we can individually try to correct each individual point and then average them all together to get the equivalent of what would be about 6 transit durations of a TRAPPIST-1 terrestrial planet. So again, I've mentioned that we can measure the temperatures for these, so we've done that, and I'm showing this temperature evolution here. You'll notice that all of these temperatures are much lower than that canonical 9 to 10,000 Kelvin blackbody, and these tend to peak at around 4 to 5,000 Kelvin, and they go as low as under 2,000 Kelvin. And so the benefit of having so much, just a wealth of data, is that we can start to bin and produce fiducial spectra across this temperature range. And so we do that, and there really aren't any surprises in terms of the higher temperature end of the range where we get a nice short wavelength for the flare peak. There are a few surprises at some of the longer wavelengths where we see more substructure during the flare decay, which is probably due to secondary heating and line emission and other things like that that we're still working on modeling. And so now that I've introduced the data, I need to introduce our models. In the same way that we could use MPS Atlas or Murem or Phoenix to understand the spots and the faculae, we can use Radon to understand the stellar flares. Radon is a fully self-consistent, non-local thermodynamic equilibrium radiative hydrodynamic suite for flare modeling. And to illustrate how radon captures the flaring process, I've made this little cartoon here. And so just to remind you, in a flare, a magnetic reconnection event in the corona accelerates charged particles down magnetic field lines towards the surface of the star, heating the plasma. And so to illustrate this, in the left-hand panel, I'm showing an incident electron beam that's producing the flux. And the width of the beam scales with the intensity of that particle injection process. And then in the right-hand panel, also in that same blue color, I'm showing what the resultant spectrum throughout the flare is due to that heating. And so I'm also showing some previous timestamps so you can get a feel for, as the flux of the beam decreases, what the resulting spectrum of the star should be doing. And I want to point out that I've used this sort of inscrutable sounding name for this model, MF13853. And Adam Kowalski came up with this naming scheme for a very good reason, which I'll take a second and walk through. Namely, this describes the 3 parameters that we can easily vary within these radon models, although there are certainly more parameters than that. The first of these is a maximum electron flux that's producing the spectrum in the heating. In this case, 10 to the 13 erg per second per centimeter squared. The second is a minimum energy cutoff of those high energy electrons in the beam, in this case, 85 keV. And then lastly, the 3 stands for the power law index of accelerated electrons. And while that's a mouthful, it basically just means, are there more low energy electrons or high energy electrons within the beam? And so these 3 parameters can be varied to try to fit our ultimate spectrum that we observe from heating by this beam. And the real power of radon comes in now that we have a very, very large model grid enabling grid searches across extremely wide parameter spaces. So our current model grid actually spans about 4 orders of magnitude in these beam heating properties. And just to illustrate some subset of that range, I've produced one representative model in gray for each of these different model grids across this parameter space. And then I've highlighted in green a model that is a best fit for one of our nearest spectra, where I've bent the continuum so that you can see it more clearly. And then I've highlighted the line emission, including the helium-10 line, which we've just talked about in flares, so we can characterize these. And then we also have the Passion series and H-alpha and other lines as well. And so I also want to point out the same electron beam that's leading to this IR emission that we can fit with JWST spectra is the same electron beam that's ultimately producing emission across the electromagnetic spectrum, giving us an estimate of how much photochemically active UV radiation would have been produced. And so we can also start to explore photochemistry with good model fits. And so here, to illustrate that principle, I'm showing a plot from an upcoming paper by Renyu Hu and his team, showing that during flares, you would expect to see multiple decades of changes in common atmospheric species following large flare events away from chemical equilibrium. And if you look at pressures that would be probable with transmission spectroscopy, we think that this would lead to about 50 to 100 part per million changes that could potentially be detectable. So moving forward a bit, how well are we doing with radon in order to actually be able to start mitigating this contamination in the spectrum? And so there's a lot going on here. I'll take a minute and walk through some of it. So in the top panel, I'm showing where I've essentially just averaged the spectrum over all 189 of those integrations that I showed during those green points in the flare. And as you can see, we don't really get a very good level of correction doing that. Surprise, surprise. But when we fit the radon spectra to each individual model, or to each individual integration, we're able to ultimately take what would have been a 3,000 part per million flare for each of these individual integrations and come up with something like a 50 to 100 part per million residual throughout the spectrum. So there are very much still some residual noise properties that you can see here that we need to continue working on to beat down to get it down to an even better level of around 20 part per million when you're averaging over all of these. And again, I'll just point out, because this is equivalent to about 6 transits of observations, that's important because that's about how many transits you would probably need to be able to start sussing out the signals of some of these terrestrial atmospheres that you would expect that we've been talking about during this conference. You'll also notice I threw some Planck fits in here. This is because we're still working out some kinks at the longest and shortest wavelengths with radon, and so I just extrapolated using a Planck function. The other thing I want to show here is we can start to get a feel for how well we're doing in terms of whether we're eating our planet signal or not. So what I've done here is I've essentially just injected a planetary spectrum into each individual integration prior to doing any of our correction. And we're not quite able to recover the atmosphere, but there are some changes in the spectrum that are consistent with the planet. So the spectrum is moving in the correct direction, although our work is very much still cut out for us. And again, I'll point out all of this is just for high signal to noise, well understood data. We need to keep moving into more difficult regimes. So all of this is ideal. What about the non-ideal circumstances? It's important to remember that the majority of integrations that are going to be impacted by these flares occur during the low signal to noise regimes. And so what do we do here? The answer is we need multi-wavelength information, specifically with near UV or U-band observations. And the reason that that's important can be seen in this figure here, where I've simulated near spec and HST COS observations. And the color bar shows the ability to distinguish flaring and non-flaring integrations based solely on the IR. But when you add in that second band, you actually get a lever arm that helps you to characterize the lower level flux. And so one of the things we've learned in some of our other work, I'll briefly touch on in a second, is that the shape of the light curve and the UV and the shape of the light curve and the IR are related by a time integral, giving us a strong prior on what's happening in one band when you have information from the other band. At this point, I'd like to quickly shift gears and say, where are we going to get all of this information with this simultaneous UV and optical and IR information? And I'd like to introduce the Early Evolution Explorer, which is a NASA small astrophysics concept that's investigating the coevolution of young stars and planets with 3 primary goals. One of them is to study young planetary atmospheres, flare photochemistry, and then also to understand accretion. And the key takeaway from EVE is that it's a multi-wavelength successor to TESS with simultaneous near UV, optical, and IR monitoring of 10,000 young stars with 30-second cadence and about 20 to 30-day stare times on young clusters. And it'll be consisting of 3 co-mounted telescopes in each of these wavelength regimes and a 25 square degree field of view. And several other EVE members are also in the room here if you're interested in some of the other science cases. So I'll quickly just show one of our flare slides where right now our understanding of these multi-wavelength flares is limited to solar equivalent flares, but we'll be going up with EVE and investigating almost 1,000 flares at these really, really large energies that we currently just cannot probe. And I'll also go back to this slide for a minute and say that one thing that EVE will be able to do due to the simultaneous monitoring is be able to use that UV band to increase our transit detection efficiency in the TESS band or in the IR band. And here I've just stitched together a number of simultaneous SWIFT and TESS 20-second cadence observations in order to do injection and recovery testing. And since I'm running out of time, I'll just point out that we're able to move from a sub-Neptune into a super-Earth regime when you can accurately account for the flares. So with that, I'll just share our science team and leave up my key takeaways. And thank you for your time.
All right, questions for Ward while I pull up his conclusion slide. Down here in the front.
Thank you. Nope, I was pushing the wrong button.
So I was wondering, how confident are you in your, down here. How confident are you in your models being reasonably correct in the UV?
That is a very good question. Right now, during the peaks of the flares, I'm very confident because the predictions we're getting from the radon models are equivalent to those that we get from empirical scaling relationships using SWIFT and TESS. However, during the decay phase, we're running more models right now to try to explain the lower temperature emission, which is not consistent yet.
Question in the front here.
I didn't quite follow why we needed to go to the ultraviolet. I believe you, but could you explain it a little more? And in particular, the lines that are in the IR are those not sufficient proxies?
Yeah, there's a huge difference in, there's actually multiple blackbody effective temperature components in stellar flares, one of which is dominant in the IR, a different one which is dominant in the UV. And so if you don't have the simultaneous information, you don't know whether you're looking at something where you get a small peak in the UV based on the IR, a large peak. And a great example of this is there are 300 kiloseconds of SWIFT observations of TRAPPIST-1. You've seen how many flares are happening in the IR. Not one flare was detected in the SWIFT observations. What gives? So that's a good example.
We have a graduate student.
Hi, that was really cool. I was curious to know what the relative strengths of the different chromospheric indicators and their decay times can tell you about.
Are you asking what the relative strengths of the different line emission properties are? So during the initial flare, you don't see almost any line emission. It's all continuum. And then as the integrations progress, the continuum emission starts to decrease, but you start to see a pickup in helium-10-830, H alpha, passion alpha, beta, even all the way out to like bracket beta and bracket gamma.
And do you have a favorite mode for observing this with?
I would say probably nearest for the lines and near spec for the continuum.
Thank you.
All right, let's thank Ward again. And let's thank all of our speakers from this morning's 2 sessions.